actual randomized algorithms. So one thing I wanted to emphasize randomized algorithms is the book Tardosh and Kleinberg. Okay, so they have the copies from Pearson, which is going to be distributed to all of you. We highly recommend that book. Okay, so I use it in my whenever I teach algorithms course. So Corman was used to be the book for algorithms before Tardosh Kleinberg came out. Okay, and initially even we were taught with Corman. Okay, but this Tardosh Kleinberg book is excellent. It's more concise. Corman now in front of Kleinberg Tardosh seems encyclopedic. Okay, it's verbose, it's encyclopedic. It's an excellent book still, but it's more sort of an encyclopedia of algorithms rather than a book that you'll use to teach algorithms. This Kleinberg Tardosh book is an excellent book to teach graduate and undergraduate level. So I would highly recommend this book. So since you're getting the copies, try that. Okay, so just give it a shot. You will really like it. The collection of problems that are there in the Kleinberg Tardosh book, it's the best collection of problems on algorithms that you'll ever find in any book. Okay, so just try it, and if you like it, you can start using that book. Okay, so back to randomized algorithms. So let me talk about two algorithms: randomized quicksort and Kargar's min-cut algorithm. Okay, so it will be slightly at a more advanced level than the previous session. So stop me if anything is if any of the concept that I'm trying to convey is not clear. So the problem is very simple. Okay, so and I'll make it even simpler. You are given an array containing n distinct integers. You want to sort it. Okay, you are given an array n distinct integers. What you want to do is to sort it. Okay, so what we will try to analyze is something called randomized quicksort. Okay, but before we do that, are you guys familiar with quicksort? Right, so everyone here is familiar with quicksort. What is the running time of quicksort? In the worst case, it's n squared, right? Okay, in the average case, it's n log n. What do you mean by average case running time? When we talk about expectation, right? So it's expectation over some space, right? Over some randomness, right? So it's an average over something, right? So what is this average over? You're saying that the average running time is of all possible inputs. All possible. So you take the average over all possible inputs. Does that make sense? Because there could be infinitely many inputs, right?
We are assuming that the input distribution is random.
Is random.
So I'll say, okay, I'm having some n elements to solve. So I'll say, look at all the possible input combinations that I can create, and then take the average of those. And this analysis I can argue that goes for any n numbers.
Any n numbers.
But combinations
For permutations, all permutations of the inputs.
1 is to n.
Right. So okay. So here is roughly the argument. Everyone is correct. The idea, the intuition is precise, spot on. No problems with that. All the inputs, we can say that all the inputs fall into sort of n factorial equivalence classes, right? And then you take the average over elements of this equivalence class, right? So all possible permutations, if you take the average, then you get n log n. So that is the idea of an average case running time, right? So whenever you talk about an average case running time, the averaging is over the inputs. Okay, so you average over the inputs. Okay, so good. So now let us talk about randomized quicksort. Okay, so here's the algorithm. The algorithm is very simple. So if the array is size 1, you just return the array, nothing to do, it's sorted. If it is not sorted, okay, so you're getting an array. If it is not sorted, then you randomly pick an index I. Okay. Now what you do is you create two arrays. Let's call it AL, okay, and AR. In AL, you put all the elements from the array that are smaller then A of I. Okay, so then this element. In AR, you put all the elements that are larger than this element. Okay, that's what you do here in these two lines. Now, you just make a recursive call. Okay, you randomize quick sort this array. Let's call that BL, and then we call that BR. This is what you get if you make a recursive call. So these are sorted arrays of the left part and the right part, and then your output is just you put A of I here, okay, and you output this, right? So that's what you do here. Simple, right? And this works. Can you prove that this works? That this is correct? The proof of correctness is not a problem, right? So you can build a sort of an inductive argument showing that this always works.
Difference would it make making it randomization and turning randomization into a what difference would it make? Otherwise, you pick up the last element and place it in the proper order.
The worst case running time of return, suppose we didn't use randomization, right? So the worst case running time is n squared, right? Here, what you will claim is that the expected worst case running time is n log n.
Yes?
N log n.
Means worst case also would be n log n.
In expectation, right? We cannot make any deterministic statements because our algorithm uses some randomizations, and our output or the behavior of the algorithm depends on the random bits that it uses, right? So we cannot make statements like the worst case running time of this is. We have to make some statements like the expected running time of this algorithm is something, right? And that is where we get an advantage. We can show that the expected worst case running time is going to be order n log n. Okay, so let's analyze the running time of this algorithm. So let Tn denote the expected number of comparisons that is performed. Okay, let's just count the number of comparisons, right? Because that basically dominates the running time of this algorithm. There are a few nuts and bolts here and there, but they don't dominate the running time. The running time is dominated by the number of comparisons. So if it's sufficient to just count the number of comparisons, right? So Tn denote the expected number of comparisons that is performed by the algorithm. Okay, now I want to claim is that T of n is equal to n minus 1 plus this expression. So why do you have this? Can you explain this expression? First of all, T of 1 is equal to 0, right? No comparisons needed if you have an array of size 1. So that is a simple base case. But why is this recursive case true?
Once the pivot is filled, so n minus 1 comparisons we need.
Okay,
We have now two partitions.
right, exactly n minus 1 elements, and it has to, all of them have to be compared with this, right? So that is where this comes from, n minus 1. Okay, so what about the second part?
And now these partitions, I'm not sure what is going to be the size of those partitions. So it can be any I, but I need to multiply it with the 1 by n is actually taking adding the probability factor into consideration.
Right? So with property 1 over n, the I could be this one, the first one. Okay? The probability 1 over n, it could be the second one. Probability 1 over n, it could be the third one, and so on and so forth. Whatever it is, this n minus 1 will come out, right? Because you need to sort of split that into two parts, right? So now T of n is equal to n minus 1 plus 1 by n. So I can write this summation, I can expand the summation, right? And this is basically the time, the expected time to sort the left or the AL, and the expected time to sort the AR, right? So that's why you get T of I and T of n minus I plus 1. So there is a slight, okay. So with property I, you pick the ith smallest element, right? So that was a, so I think it follows. If I go into the details, you'll get confused rather than becoming clear, right? So this expression holds because with property 1 over n, it could be the ith, what you picked is the ith smallest element. So in that case, you will need to sort the array that is the previous and the array that is on the right hand side. So this is the expression that you get. Okay. So is this true? Just following from this. So T of n is equal to T of n minus 1 plus 2 by n times this summation.
We are assuming that both the parts are calculated to be equal, that the partition is equal.
No, we are not assuming that the partitions are equal. We're just simplifying this expression. We're just simplifying the expression on the right hand side. So if you're convinced about claim 1, this is just simplification, nothing else.
Summation I we are taking from 1 or from 0.
I equal to 1
Make
or
it symmetrical.
okay. No, so why should it be? So we are sort of with property 1 over n, it's the ith smallest element. So it goes from I is equal to 1, 2, 3, 4.
It means if the two summations become equal, the two summations, that's what you're saying.
The T of I and T of n minus I minus 1, we are saying they are actually identical but in the reverse order. T.
These two summations you
CR
get
is
to
the runtime, is the time required to sort ith an array subarray of
Size I, right?
So the left subarray can be size 0 itself, right? If the first element is the pivot with probability 1 by n, then the size of the left subarray would be 0. So T is 0. It should be T 0.
Okay. So yeah, so there might be a some, yeah, so you're right actually, it could be 0. N minus 1. Yeah, it could be, yeah, so the summation should be from 0. Yeah, you're right.
But maybe if you are not listing T 0 because 0 number of comparisons,
Then the T of
n minus 1.
the summation
n
of
minus 1 is that
T 0
when I is n minus 1, then n of T of n minus I minus 1 is actually representing T 0.
it's okay, just the
Yeah, I think it's, yeah, so this just put a 0 over here, right? So it's fine. Yeah, so I'll make the correction. Okay, so how do we solve such reconciliations? Any idea? So how do we solve the simpler reconciliation? Perhaps that was covered in the first session today. So how do we solve like Tn is equal to 2Tn by 2 plus big O of n? How do we solve those? By substitution, right? So, or master theorem, which is basically proved by substitution. But this is slightly complex, right? So this is weird looking. So you have Tn on this.
As far as I am able to understand, since we have in the first claim 1, we have partitioned the array into two parts. One containing I values and the other one containing n minus I minus 1 values. In the second one, we are assuming that the pivot value is getting placed at the center. So if we are saying that both the partitions are equal.
No, we never made that assumption. No, we are just simplifying this expression, right? So just expand. Okay, so if that is causing confusion, so let's just expand this expression, right? You expand the summation. Let's do it.
T of 1 and then T of n minus 2.
Which will be then each
T n minus 2 and then T of 1.
Okay, so let's do it. Okay, so this is going to be, let's put I equal to 1, I equal to 3, I equal to 4. Okay, so then what do you get? So we get T of 1 plus T of n minus 2.
Start from 0.
Okay, so I is equal to, we starting from T, we are putting I equal to 1, right? Oh, again the same thing. Okay, so let's put I equal to 0.
No, there was a reason to do that because we want to say that the two sums are same. Even I'm not sure whether it should be 0 or not.
Yeah, so even I am not sure.
No, it's okay.
So let's
Yeah, just.
When we are since we have placed one pivot value at the position which we have been complete by n minus 1. What is n minus 1? We are placing one of the values at its actual position. So won't the summation be covering that particular value and considering the other n minus 1 value starting from 1 to n minus 1? Because one value has been placed at the actual position by n minus 1 values.
no, so okay.
Is the first
Is this clear to you? Why is this true? Because if this is clear to you, this is just a simplification, right? So if this is clear, then this is just a simplification, right?
The confusion is we are counting that why I should be removed from 1 or 0.
Okay.
We are placing one of the values at the position,
Okay.
and the other n minus 1 values are there.
Okay.
So we are starting the index from 1 and starting till n minus 1.
Okay. So it's, if I replace it with 0, is it clear to you? Is it? No, that's not.
That n minus 1 is referring to the nth value. N
That-
minus 1 comparison in Tn is
N
referring
minus
to the
1 is
nth
the
value.
partition, no?
It is referring to the nth value. Now that what is the size of the
Is it?
So there are two partitions.
So
Pi is size of one C value and P n minus I value is size of second number of elements. And pivot is left out of these sub-values. Hold on.
Okay. So let her.
Let him take it.
Yeah. Okay. So is the fact that I is equal to, the summation is from I equal to 1 to n minus 1, is that causing the confusion?
that is right. Means you are getting you are discussing now that whether I should start from 1 or whether it should start from 0. I feel that it should start from 1 only.
It should start from 1.
1, not 0.
Okay. So it's okay. So the tiny little detail is how you're dealing with this, right? So the way I'm doing it, I think I made a mistake there. So the way I'm doing it is I pick the ith item, okay? So I can maybe just scrap this whole thing and redo the entire calculation, right? So I'm picking the ith item, I'm putting all the elements that are less than this on this side, and I'm putting all the elements that are more than this on this side, right? Yeah, so and I'm keeping it aside. I'm putting this sort of separately, right? So let's derive this. Let's forget about this and let's derive it completely. Okay. So now with probability 1 over n, your the pivot that you pick is the first smallest number. Okay. So in that is the case, then you have 0 elements on the left hand side and n minus 1 elements on the right hand side. With probability 1 over n, it is the second smallest, then you have t1 here and t of n minus 2 here. Okay, so let's resolve that. Okay, so with probability 1 over n, you have t0 and tn minus 1. With probability 1 over n, you have t1 and t of n minus 2. And similarly, the nth item, if you pick with probability 1 over n, you pick the nth smallest item as the pivot, then you have t of n minus 1 plus t of 0. Okay, so now it's clear. So you have a summation from 0 to n minus 1. Okay, so yeah, so there was a mistake, and this is exactly what we have been talking about, right? So this should be 0. Okay, so this is the expression that you get. Yeah, so I'll make the change. So this should be 0 to n minus 1. Okay, and so if you take all these things together, then you'll get 2 of all the quantities, right? Am I right, or yes? So for simplification, just assume that n is favorable, it's even or odd, whatever whatever makes the case simpler, right? So we don't want to delve into the detail of what if n is odd or what if n is even. Okay, so then this is going to result in this particular expression.
I is equal to 1 or I is equal to 0?
I is equal to 0 to n minus 1. Huh? Okay, so I is equal to 0 to n minus 1. Okay, so how do we solve such complex reconciliations? No, how do we? I'm asking a question. How do we solve such reconciliations? So you got a reconciliation, right? You have to solve it to get the value of t of n. How do you do that? Oh, if you try doing substitution, then the expression becomes very complex, right? So you have here t1, t2, t0, t1, t2, t3 up to t of n minus 1. So what are you going to substitute? So it becomes very complex very quickly. So if you keep expanding it, then it becomes very messy very quickly. So how do you do that? How do you solve such reconciliations? Use for Master's theorem. So the template that you use is t of n is less than equal to or equal to a t of n by b plus c times n to the power k, right? This is the template. Can you fit that template in this reconciliation? You can't, right? Because it's very complex. It's more complex than that, right? So this has t1, t2 up till t of n minus 1 here. t0, t1, t2 up till t of n minus 1. So it doesn't fit into the template of the master's theorem. You can't use the master theorem. So what do you use? What do you do?
T of I, which is nothing, we are denoting it nothing but the expected number of comparisons.
Okay.
So if we replace T of I by expected number of comparisons and obviously random variables defined correctly, I'm not sure.
No, so right now we are in the domain of solving reconciliations, right? Forget about randomized. This is a reconciliation, nothing to do with randomized analysis anymore. It's a simple mathematical question. How do you solve this reconciliation? Okay, I want to get a closed upper bound for T of n, a closed form expression for T of n. So what is the technique that you use if your reconciliation becomes very messy as this? You remember the guess and check? You guess the value of T of n and then you prove that that guess is correct. How do you prove that your guess is correct? By induction. Okay. So you make a guess for T of n and then you just use induction to prove that your guess is indeed correct. Okay. And the guess that works in this particular scenario turns out to be n log n. That means what do you do? Well, you want to show that T of I, okay, is less than equal to c times I log I. Okay?
I guess the government book terms this guessing thing as, they call it substitution.
They call it substitution, yeah.
Yeah, exactly.
Yeah.
So probably somebody answered substitution. I guess that is.
Right, okay, yeah. So if somebody answered substitution, okay, so they call it substitution. The common book, even the Kleinberg Tardosh, I think they call it the substitution method. Yeah, I think they call it the substitution method. They call the. Yeah, so the thing that where you use the expansion, they call it the unrolling of the recursion. Sorry, yeah. So they call it the unrolling of the recursion, and this guess and checking is called the substitution method.
Like the master method, there used to be Akrapasi method where we used to have an integral and then bounded. Something in that also. I remember studying, just like if you have a master method, there used to be Akrapasi method where if you have a summation in this, so you could bound it using an integral. I don't remember exactly what the expression used to be.
Okay. Yeah, so even here, when you do a substitution, you try to guess and check. You will end up integrating, right? Because whenever you have these kinds of summations, and you have these expressions of I log I or 1 over I, it's better to do, it's easier to just do integrals and then just do a bounding. Exactly the way we did 1 plus 1 by 2 plus 1 by 3 is roughly log n. Those are the kinds of tricks that you will use. Okay, so when you do that, okay, so you guess that T of I is less than equal to for some constant c, T of I is less than equal to c times I log I. So first you plug in, first you check that this is true for the base case, okay, and then you use the inductive method. So that means this is true for I equal to 0, 1, 2 up till n minus 1. So that means now you can replace all these quantities T of 0, T of 1, T of 2 with c times corresponding I log I, and then do kind of simplification integration to show that T of n is indeed also less than equal to c times n log n, and then by induction, by the induction argument, you conclude that this guess is indeed true. Okay, so if you do that, all those complicated calculations, then you'll find that T of n is less than equal to c times n log n for some constant c. Okay, so let me not go into the messy details because it might end up with the I equal to 0 situation. So, okay, so let me not go into the messy details of the calculations. If you do that, you will get T of n is equal to less than equal to c times n log n.
How do you make a guess in this case?
Yeah. Um, in this particular scenario, there are other ways of analyzing this randomized quicksort. So basically, you get a sense of, okay, so you get a rough sense of what the actual running time should be, right? And the rough sense that you get what the running time of this randomized algorithm should be is that, suppose here's an intuitive analysis of randomized quicksort. Suppose you happen to pick a pivot that is the middle element, the n by 2th smallest element. Then you get n log n. Suppose every time by some magic you are able to find the middle element always. Then you get n log n, right? Because you are sort of breaking two equal parts and you get behavior very similar to the merge sort. Suppose you don't, the magic doesn't give you the middle element, but roughly the middle element. Okay, so you get, say, an element between 1/3 and 2/3. What is the running time? Still, it's n log n, right? And now you sort of get a rough sense, okay, so that every time you are creating a split, there is a very good chance that you will pick an element that is going to be a good pivot, that is going to be between 1/3 and 2/3, right? And then you do some probability calculations and then you try to figure out that the expected running time should be n log n. And then once you have that intuition that this is roughly n log n, then you perhaps go back and even sort of analyze this. So, but I don't have a crisp answer for that, right? So it's sort of a guess and check. So I get this question every time I teach these kinds of things from students. How did you guess that? How did you, what magic? Well, it's just a hit and trial method. Okay, so these are very, very complex reconciliation in general, and it's hard to guess unless you do a little bit of hit and trial. It's hard to know what the real answer should be. Okay. Okay, so here's another interesting way to analyze the same randomized algorithm. Okay, so let's do this. So for I less than j, let xij be a random variable that is 1 if a comparison between ai and aj is made during the algorithm, while executing the algorithm, and 0 otherwise. If a comparison between ai and aj was made, then this variable is 1, otherwise it is 0. Okay. Now, I want to claim that the expectation of this random variable xij is 2 by j minus I plus 1. Okay, so why are we interested in this? So forget about this claim for a moment. Why are we interested in this random variable? We are interested in the expected running time or the expected number of comparisons. What is the expected number of comparisons in terms of these random variables xij? Summation of xij. Okay, so this is the quantity that we are interested in. So x is summation I less than j xij. We are interested in the expectation of this quantity. We are interested in the expectation. So if we are able to find the expected value of xij for any ij, then we get the expectation, right? That's exactly why we are interested in this. Okay, so now let's get back to this. Why do you think the expected value of xij should be this quantity, 2 by j minus I plus 1?
There is a comparison between EI and AJ only if one of them is picked as a pivot.
Okay.
So 2 comes as because of either AI can be pivot or AJ can be pivot.
Okay. Okay. Okay.
Also we can claim that they will never be compared if any element between AI and AJ
Okay.
is ever chosen as a pivot.
Okay.
That means none of the elements from AI to AJ, of course in the correct, in the original, in the sorted one.
Okay.
None of the elements from AI to AJ were ever selected as a pivot, and that comes on what is the probability
Ever as in prior
to this.
Okay.
So there are actually j minus I plus 1 such elements between I and j.
Mm-hmm.
And out of this, either AI or AJ was the first one to get picked as the pivot, is
Okay.
actually 1 over j minus I plus 1.
Okay. So okay, so all your statements sound correct. So let me go back to each of them. So this is the ith element, this is the jth element, right? Now, suppose, okay, and we are looking, so the way I've defined, I think it's going to be problematic. No, this is again going to be causing issues. Okay, so let me redefine this variable xij. Okay, so this makes more sense, right? So xij is a random variable, just cancel this. So xij is a random variable which is 1 if a comparison between the ith smallest and the jth smallest element is made and 0 otherwise, right? So this makes more sense. So now we are looking at the elements of the array in a sort of sorted manner. So this is the ith smallest and this is the jth smallest. Now, if I pick a pivot which is between the ith smallest and the jth smallest. Suppose I pick a pivot which is this number, okay? Then is there going to be a comparison between the ith smallest and the jth smallest in the entire duration of the algorithm? No. The comparison is not going to be made. Now if you pick the ith or the jth element, is the comparison going to be made? Yes, the comparison is going to be made. If you pick any element here or here, what happens then? At that time instant, it sort of gets deferred, right? In the future, it might or might not get compared. So in the next round, again the same thing happens. If you pick it between I and j, it will not be compared. If you pick I and j or j, it will be compared. And again, if you fall out of I and j, it gets deferred to the next round. Okay. So what is the probability that I and j is going to be compared? Okay, so the probability, if you think about it a little bit, the probability will come out to be either you pick I or you pick j, okay, and you divide it by the total number of elements between I and j included, right? Because that is the time instant at which this game is going to end. Right? The game is going to end only when you pick the pivot between I and j. Right? It's slightly tricky, I know it, but it's not very difficult to realize that this game continues. Look, if the pivot that you pick falls out of the range of I and j, then the game continues. If it happens to be inside, then the conditional probability is 2 by j minus I plus 1. Given that the pivot falls in the range, the conditional probability is 2 by j minus I plus 1. If it falls outside, the game continues. And the conditional probabilities always remain the same. So the overall probability that these two elements are going to be compared will be equal to this particular probability 2 by j minus I plus 1. Okay. So the expected value of this random variable xij will be 2 by j minus I plus 1. This is the length of the interval between j and I, and this is the that you pick either I or j, then these will be compared. So the expected running time is going to be this expectation of the summation I less than j xi of I of j, which by linearity of expectation, that's the first result that we got, is going to be just the summation of expectations, and then we just use this. Okay, so if you take the summation over this, then this is the kind of expression that you get, and we know what this kind of summation looks like. It's always we are upper bounding it, right? So these kinds of summations always result in sort of log n. So what you get is 2n log n. Right, crude upper bound. Okay, so for some values of I, it will be smaller. Okay, it will not be 1 by 2 plus 1 by 3 plus 1 by 4 up till 1 by n, but still we are bounding it all of them by log n. So you have n because coming from this summation, and all these terms we are bounding by log n. Right. So again, use of the inequality obtained from the integral that you learned in the first session. Right. Again, the same inequality that we have. So again, we get a different way of analyzing the randomized quicksort algorithm. The expected running time or the expected number of comparisons is going to be n log n.
N, I'm missing something. N coming from?
Okay, so let me see. So it's the way we are doing it. Okay, so let me.
And one is missing because of that.
No. Okay, so let me see. Okay, so you have this array, right? So suppose this is you do from, so it's sort of I less than j, right? So you fix I is equal to 1, and then you vary from j is equal to 2, 3, 4, 5 up till n, right? So let's see. So you will have I equal to 1 and j equal to 2, right? So you will have.
It's okay. For every term, it's log n.
Right. So for every term, yeah. So, yeah, I'm just hoping that I'm not again making the I is equal to 0.
That was not right.
Okay. I might be, so because sometimes I just write in a sort of a rough sense, and there might be a mistake. Okay. So again, so from a completely different analysis, you get that the running time of randomized quicksort in expectation is order n log n. Okay. Yes.
Do we refer to natural log or log to the base 2?
Here.
Maybe natural log, but in general, when we teach this quicksort, I refer to log to the base 2.
Yeah, but if you write in order notation, it doesn't make a difference, right?
It won't make a difference in that.
Right.
In general, I just want to clarify that in serial, like a quicksort, when we discuss the complexity of the quicksort, it refers to log to the base 2, right?
Yeah, it's, we typically in computer science we write log to the base 2.
Because we are bisecting the
dividing.
array, we are dividing it into two parts.
Here there is a, yeah,
In
but
this case, that's different. In this case, that's different. Just read this. In general, it would be, if I'm teaching in the class, that shall they ask me the complexity. Shall I refer to natural log? If we are talking about bigger notation, then it's fine. Natural log is fine. But in general, would it refer to log to the base 2 or in natural log?
look, so if you are writing it in bigger notation, it doesn't really matter, right? Okay, so suppose okay, so it's a good question, maybe algorithms question. Suppose we are talking about merge sort, right? And in merge sort, you split the array into two equal parts, right? What if we split the array into 1/3 and 2/3? Okay, so I'm just trying to clarify that the 2 is not something that is very important, right? So if you split the array into 1/3 and 2/3 and do the same merge sort routine, the running time that you will get will be order n log n again, but the base of the logarithm might be different, right? Okay, so basically the base is not very important when you express it as a, but in some other cases it might be. So for example, this is a typical example that I give in my algorithms course. So remember binary search, right? So binary search, if you count the number of comparisons for binary search, the number of comparisons is log n base 2. Suppose I run a different algorithms. Okay, suppose I change the algorithm a little bit. I want to find, this is a sorted array, I want to find x. I figure out, I compare, I break, instead of breaking into two parts, I break into three parts. And check which of the three parts this x belongs to. And then sort of zoom into, no, that's what I'm trying to, no, that's not correct.
Sir, I mean to say, like you said, quicksort. Binary search, yeah. In binary search, we basically divide the array into two parts, every time. So that's why it's
Well, you have to do the calculations, right? You write the reconciliations and solve that. Right, okay, so you're claiming that the runtime of this algorithm is going to be log n base 3? Okay, so that's better than binary search?
That in one sort.
It's better than binary search, okay? Then why don't we do a ternary search? Okay, so then if you break it into 4 parts, then it should be log n base 4.
But dividing into 4 will also takes more parts.
Okay, so that's why that's what I'm saying, right? So you have to be careful. If you count the total number of comparisons, the worst case, is it log n base 3? I'm forgetting about the big O notation. I'm not talking about the big O notation. I'm talking about the exact number, the worst case number of comparisons that you need to perform. In binary search, it is log n base 2. Here, is it log n base 3?
So like in 3, if we have more than 2 child, so then.
That's what I want to challenge, right? So it's not log n base 3 because it causes a contradiction, right? If it is log n base 3, then it is better than binary search. Then what stops us for dividing into 2 parts? We can divide into 10 parts. Then it will be log n base 10, even better. And what stops us from there? Divided in n parts will be log n base n, 1. That's ridiculous, right? There's something going on. It's not that you divide it into 3 parts and that gives you log n base 3. There's something more going on, right? You have to be careful. So what do you think? Okay, let's forget about this. Let's work on this. What do you think is going to be the worst case number of comparisons for this algorithm? 2 log n base 3, which is actually worse than binary search, right? And that's why. So it's not the way you divide it. It also has to take the constants that are involved in the reconciliation. Those are also important, right? So here the reconciliation that you get is T of n is equal to
This is log 2n.
this one? No, this is natural log. Natural log because the summation was natural log, right? We took the integral, and whenever we take the integral, it's natural log, right? But again, if you write it in big O notation, it doesn't really matter. Okay. Okay, good that all these issues are being brought up. Okay. So this is the first algorithm that I want to talk about, randomized quicksort, and let me talk about another algorithm. It's called it's called the Karga's min-cut algorithm. The problem is very simple. You are given a graph, undirected, unweighted graph, okay, and you want to find the cut in this graph of minimum size. So what is a cut? Well, a partition of vertices. Everyone familiar with graphs, right? So I can assume that. So a partition of vertices into 2 non-empty sets is called a cut. Okay, the edges between the vertices in different sets are called cut edges, and the size of the cut is the minimum number of such edges. Very simple, right? So a cut is partition of vertices into 2 parts, into 2 sets. The cut edges are the edges that go from one side to the other side, okay, and the size of the cut is the number of edges go from one side to the other side, right? So the problem is this: you are given a graph, you have to find the cut of minimum size in the graph. Okay, there might be multiple minimum cuts. You are supposed to output any one of them. So if we just talk about this particular example, can you give me a cut of minimum size in this graph? 2. Okay, so when I say give me a cut, that means you have to give me a partition. So you're saying that the size of the minimum cut is 2, but what is the cut? Okay, so you put everything here in one side, on this one. Okay, so that's the cut of minimum size. Okay, so the problem is clear. So here is, I'm going to define, okay, before we talk about that, before we start talking about Karga's min-cut algorithm, do you know how to solve this problem by any other means? Do you know how to solve the min-cut problem, find a min-cut of a graph?
Just testing it to
Huh? Max flow min-cut? Well, have you ever heard about the max flow min-cut theorem or the max flow algorithm? Okay. Okay, so there is a deterministic way to solve this problem. There is a way to solve this problem. Okay. So we don't need to talk about randomized algorithm. There is a deterministic algorithm that solves the problem. Okay, it's based on max flows or the max flow min-cut theorem. But okay, so let's not go into that and talk about a randomized algorithm for this particular problem. So for defining the randomized algorithm, I have to define some simple steps. Okay, so let me define a simple step of the randomized algorithm. It's called a collapse step. Okay, collapse an edge. Okay, I'm going to define something called a collapsing an edge. Okay, so what you do is you merge the vertices. Suppose you're talking about an edge UV. Okay, so you're talking about a edge UV. So collapsing that edge means that you merge vertices U and V and you remove the self loops. Okay, the resulting graph may have multiple edges between the same vertices or a multi-graph, but that is fine. We're going to save information about all the multi-edges, all the edges of the graph. Okay, so for example, if you collapse this edge, then this is the graph that you get. Okay, make sense? Okay. Suppose, and again, I choose another. Okay, so here's the min cut, the Kargas min cut algorithm. Like this is we're going to modify it a little bit to improve the running time, but the rough idea is completely captured in this particular pseudocode. So algorithm is the following: you repeat this procedure n times. Okay, so let's talk about what is the procedure that you repeat n times. While the number of vertices in the graph is larger than 2, you pick a random edge. Okay, in the multigraph G, the current multigraph G, and you collapse that edge to obtain G prime. And then again you set G equal to G prime, and you keep looping. Again, you pick a random edge, you collapse it. Okay, you get a new graph. Again, pick a random edge, you collapse that. Again, you get a new multigraph. Again, pick a random edge in that multigraph. Again, collapse it. Continue doing it until there are only 2 vertices left. Okay. Now, there are 2 vertices and all the edges. Okay, so these 2 vertices, these are sort of vertices which contain all the collapsed vertices of the original graph. So they form a cut. And the edges between these 2 vertices form the edges of the cut, right? So you do this whole thing. So every time you come out of this while loop, you will have a cut. You will have a tentative cut, a prospective cut. Okay? So you repeat this whole thing p times. Okay, every time you run this while within the while loop, you will get a cut. So you will get p cuts, different cuts, if you run it p times. What you do is you pick the best one out of them. Okay, so the algorithm is the following: you repeat something p times, and this something is the following: you keep collapsing until there are 2 vertices. That gives you a cut. Okay, and out of p cuts, you pick one that is the minimum size, and you just output that. Okay, so that is your randomized algorithm. Okay, so let's run this randomized algorithm on this particular example, right? Suppose you pick a random mesh to collapse, right? You start. So this is just one time. Okay, so you pick a random mesh to collapse, you collapse them. This is the graph that you get. Okay. Again, you pick a random edge, maybe this one, and you collapse. This is the graph, multi-graph that you get. Again, you pick a random edge, you collapse. This is the graph that you get. Right. And once you have 2 vertices, all the cuts that are between these 2 vertices form the cut. Okay, are the cut edges. Okay, and you repeat this p times. Okay, so this is just showing how the algorithm works. Now here's the statement I want to claim: the algorithm does well if the edges across a min cut is never picked for collapsing. Make sense? If during this collapse procedure none of the edges of the min cut are ever picked, then these edges survive. Okay, all the edges are going to survive, and eventually you are going to output this min cut. Right? So algorithm does really well if none of the edges of the min cut are picked during the collapse procedure, because at the end they are all going to survive, and that is going to be the min cut. Right? Okay. So let's do some calculations. Let's try to see what is the probability that this algorithm is going to actually output the min cut of the graph. There might be many min cuts in the graph, minimum size cut in G. Let's fix a minimum cut. There might be multiple minimum cuts. We want to output one. Let's fix a minimum cut C. And we do an analysis with respect to this fixed minimum cut, minimum size cut.
I have a question.
Yes.
What if among those P trials we don't get, how do you fix P? What if among those P trials we don't get the cut of minimum size? How do you choose?
We are going to bound the probability. We are going to fix P. Okay, we are going to cleverly choose P so that the probability.
Very small, I might not get.
Exactly. So if P is equal to 1, the probability of outputting a min cut may be very small. So that's exactly what we're going to do, right? So we're going to do the probability analysis. We'll pick P very cleverly so that the probability that this algorithm outputs a cut of minimum size is really large.
But entirely depends on.
Another say like that, we repeat the process till we get to what is this? Then
Until we get?
two nodes at the end. Why not we say like that?
No, we always, within the while loop, we always,
Two nodes at the end
no, so,
with connected.
so within the while loop, we always run it until there are two nodes, right? But we repeat this procedure of collapsing into two nodes P times, P different times, right? Just to enhance the boost the problem.
Very rough, P can very rough.
We will figure out that P depends just on the number of vertices. We'll fix P just depending on the number of vertices as a function.
At the end we get two nodes left. That is sure.
That is sure, yeah, because in the while loop we are running it until we get two nodes left.
So why not we concentrate on that? What we repeat the process till we have two nodes.
No, but we are doing it, right? Within the while loop we run it until we have two nodes left. That gives us a cut. But we then run this whole procedure starting from the original graph P different times, independently P different times, just to boost the probability. Because if we do once, the probability might not be significant. Okay? We're going to do the analysis and pick the P very carefully. Okay, so let me ask you this. What is the probability that a randomly chosen edge belongs to this fixed minimum cut C? Okay. So, does this make sense? I'm trying to make a statement that the probability that a particular edge E, okay, a randomly chosen edge E, is in the minimum cut is less than or equal to 2 by n. Okay, why do we get that? Well, because the number of edges in the graph, which is denoted by modulus E, I'm claiming that that is greater than or equal to n times C by 2. Why is this? Suppose, suppose this is true. Then is this true? Suppose the number of edges in the graph is greater than or equal to n times C by 2. Then this probability is less than or equal to 2 by n. Is that clear? Right, because the probability that E belongs to C will be the size of C divided by the number of edges. Right? So, probability that E is in C is going to be equal to C divided by E, right? And if E is greater than or equal to n C by 2, then this is going to hold, right? So how do you get that this is greater than or equal to n times C by 2? Why is this true? Okay, take a half a minute and think about it. Why should the number of edges be greater than or equal to n times the size of the minimum cut divided by 2? No, we don't have any requirement like that, right? Okay.
And consider the following split of the graph. One that the node that you have chosen is on one side, and the other partition consists of all the other nodes.
Right. So yeah, so pick any one node, and suppose we call the node I, right? And we denote di to be the degree of that node, the number of vertices, the number of edges that are starting from that node, right? What do we know about the degree of di for any I?
More than C.
Di is going to be greater than or equal to C, right? Because otherwise there will be a min cut of size less than C, which is a contradiction, because the min cut we have the size of the min cut is C, right? So this holds true. So the degree of all the vertices is greater than or equal to C. So why is this, the number of edges in the graph, greater than or equal to this? What is the sum of degrees of all the vertices in the graph? Summation of the degrees of all the vertices in the graph is exactly equal to, so summation for any graph, summation of degree is equal to twice the number of edges, right? And so you combine these two facts, you get that this holds true. Okay. So the probability that a randomly chosen edge will belong to the min cut is actually quite small. It's 2 by n. Okay, so there is a good chance that you pick a random edge, there is a good chance that it will not belong to the minimum cut. So if you collapse, you have still not done any harm, because you have not sort of killed the minimum cut, any edge of the minimum cut, because with good probability the edge is not belonging to the minimum cut. Okay, so this we have done. So if E is not in the minimum cut C, then size of the min cut of G prime is the same as the size of the min cut of G after performing a collapse on E, right? Make sense? I'm not saying anything fancy, right? If this edge that you pick to collapse does not belong to the min cut, then the size of the min cut of the new graph after collapsing is the same as the size of the min cut of the original graph. That does not change. Okay? Okay. Okay, so let's do some probabilistic analysis. Let di denote the event that none of the edges in C have been used in the first I iterations. Okay? Di is the event that none of the edges in C have been used in the first I iterations to collapse. Okay? So we are interested in this quantity d of n minus 2. None of the edges has been used in the collapse up till step n minus 2, right? This is the probability that we are interested in. We can write this probability in this particular conditional probability in this particular manner. Okay, so it might be slightly tricky. So if you are familiar with conditional probabilities, then this should not be a big surprise. Okay, so we can write this as this particular conditional probability. Let's just focus on probability di plus 1 given di. That means you have not used any edges from the min cut up till the ith step. Conditioned on that, you will not use any edge from the min cut in step I plus 1. What is that going to be? Okay, so d, basically d. Okay, so what is d or d1 or d2 given d1?
So far I've got this thing.
Yeah,
The possibility is 21.
yeah, d2 given d1. What is the probability that d1? What is the probability of d1? Because I'm writing it in a shorthand notation, right? So eventually, if you telescope it, eventually it will also have the term. I'm writing it a shorthand notation. This is not very precise, but eventually it will also have a term probability of d1, right?
D1 would be n minus c choose 1. You don't have to pick an edge from the cut, right?
d1 is you do not pick an edge from the min cut in the first step. Okay, so that follows from here, right? So it will be 1 minus 2 by n, right? And then after d2 given d1, what is that going to be? it will be something like this, 1 minus 2 by n minus 1, because the number of vertices have shrunk to n minus 1. And you keep doing this, right? So again, it will be 1 minus 2 by n minus 2, 1 minus 2 by n minus 3, right? So there's something imprecise here, but I just want to convey the intuition rather than go into the details of the calculation, right? So it is initially 1 minus 2 by n. After shrinking, the number of vertices becomes n minus 1. So the probability of again doing the same thing is going to be 1 minus 2 by n minus 1, and doing that dot 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 until 1 by 3, right? So don't get lost in the on the precise statement. There's some imperfections here, but the idea is there. Okay. So how do you solve? What do you think this expression is going to be? Can you simplify this expression, this kind of expression? So what do you get if you simplify this?
Term actually simplifies to n minus 2 by n.
Okay.
Similarly, when we multiply all of them, तो बहुत सारी terms कट जाएगी.
Exactly, that's what I'm saying, right? So okay, so let's see. So this is n minus 2 by n. Right. What is this? This is n minus 3 by
n minus 1.
By n minus 1. What is the third term?
अब नीचे की सारी denominator terms कटना शुरू हो जाएंगी.
Okay. Right, so see, the terms are getting cancelled now, right? So this gets cancelled, 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 this gets cancelled. So, okay, so what do you get eventually? N minus 1, right? So it's a sort of a telescoping product, so you keep cancelling, and eventually what is going to survive is just 2 by n times n minus 1, right? So that is omega of 1 over n squared. Okay, so now, so the probability that none of the edges of the min cut will be used during the execution of this while loop is at least 1 over n squared, right? So it's at least 1 over n squared, but it's really small, right? There's a good chance that an edge will be used. The n edge will be used with probability is at most 1, is roughly 1 minus 1 over n squared, right? So how do we, so now do you get a sense of what this P should be, so that with a good probability this min cut, Karga's min cut algorithm will output this particular min cut? Now this should give you a hint of what our choice of P should be, right? Because in one iteration the probability of outputting this min cut C is at least 1 over n squared. So how many times should we repeat it so that the probability of outputting this min cut gets increased? Order? Okay. Right, so if you do it order n squared log n times, then we can actually show that it's a significant chance that you output correct answer. Okay. So if you pick P to be n squared log n, okay, so let's pick P to the order n squared, P to the n squared log n. Now let's calculate the probability that the algorithm returns the correct answer. That means returns this fixed min cut C. Okay. So the probability that algorithm returns min cut, this min cut C, is going to be 1 minus 1 minus 2 by n squared. So basically this, roughly this is what we get here, to the power n squared log n, because we are repeating it n squared times, n squared log n times. is just probability boosting, right? If we have a certain chance of success in one trial, to boost the probability, what we do is we run multiple independent trials, okay, and then pick the best one out of them, okay, and the probability that the algorithm does not return a good answer, okay, will be equal to the probability that the bad event happens in each of the independent trials. So the bad event happening in each of the independent trials will be bounded by this term, okay. So 1 minus that will give you the probability that the algorithm, the good event is going to happen. Some very simple probability calculations, right? So there's nothing deep here, okay. So this raised to the power means that the bad event is happening, okay, all the time, right? And you subtract 1 minus, that will give you the probability that the good event is going to happen, right? And if you simplify this expression, okay, then you get something like this. Do people know what kind of inequality you use to simplify these kinds of expressions? Maybe that will also be useful. Okay, so have you seen this expression? Right? You just use this expression here, okay? So if you use this particular expression here, then you get this quantity will be e to the power minus 2 by n squared log n. So it will be 2 log n. So e to the power minus log n will be 1 over n. That's why you get 1 over n here. That's why we choose n squared log n over here, right? So since we wanted e to the power minus this quantity times this, right? So you get the probability that this algorithm returns the min cut is very large. Okay, so we have boosted it to 1 minus 1 over n. So there is a good chance that your algorithm will output this fixed min cut that we started with. Okay? Are there any questions? I think I might have lost many of you guys. So if you can go back on some, is the probability calculation clear? So at every step, okay, so if it has survived up till ith step, it will survive in the next round with the probability, yeah.
So application of min cut
Yeah, so actually min cut algorithms are used in graphics, in vision. So for example, I'll give you an example, okay. In social network analysis, graph analysis, for example, suppose you want to, okay, so what could be an example? Okay, so okay, so suppose you're talking about a cluster analysis, right? So you have a social network graph, okay, and you want to figure out what are the two clusters in the graph. And the rough intuition about clusters is that a cluster is a set of vertices, is a subset of vertices which have well developed connections between them, right? So these are two clusters of friend or two friend groups, right? You want to break this social network graph into two parts, okay, or maybe multiple parts, okay, so that all these individual groups have tight connections between them, but inter-group connections are small. So yeah, so you can model this as a min cut problem, right? Because you find the min cut, then you basically are breaking into two sort of separate groups which have tight connections. Graphics, it has gained so the exact, I have to reconstruct it in my head. So what they do is even in graphics, so for example, you're given an image, right? You're given an image and you want to sort of cluster it or separate the image, okay, into the components, right? So suppose you have this image, right? You want to break it into duster and the board, right? and you define roughly a graph with respect to the pixels. You define connections between the pixels, and it has been shown that if you define this graph carefully and you solve the min-cut problem, it gives you a nice segregation of the input, of the object, right? And it has been shown that min-cut based algorithms in graphics have shown to be a very interesting results in graphics. There are multiple other examples that I have to think about, but min-cut is sort of one of the most basic fundamental kind of problems that people use. Okay. Okay, so any other? Is the probability calculation clear? It's not very intense, right? So if you understood the first, that the probability of picking an edge from the min-cut, that was low, at most 2 by n, and what we have done is that just extended that, just realized that if in case you didn't pick an edge from the min-cut, then the size of the min-cut is the same in the collapsed graph, and if that is the case, then further on, probability of picking an edge from the min-cut is again less than equal to 2 by the number of edges in the surviving graph. So that is how you get this telescoping product, 1 minus 2 by n, 1 minus 2 by n minus 1, so on and so forth. Then you just took a telescoping product, you simplified it, get the terms that survive, that is 1 over n squared, and what this step is just probability amplification. You just did a boosting, you amplified the probability, right? So if you repeat it these many number of times, then the probability of success gets amplified to 1 minus 1 over n, okay? Okay, so now let me talk about the running time, okay, and try to improve this a little bit. So the running time of this algorithm, since you're repeating it p times, you get p times the collapsing, okay, each while loop will cost you n minus 2, because these are the number of times you're collapsing, and collapsing each time will cost you n, right? So the running time will roughly come out to be n to the power 4 log n, right, which is not very nice, given that there are deterministic algorithms that might give you better results, right? The question is it possible to improve the running time of this algorithm? We don't want it to be as bad as n to the power 4 log n. Okay, and the observation that we use to get an improvement on the running time is the following. The probability of a cut C surviving becomes smaller as the graph shrinks in size. Okay, so there is a need to repeat for smaller graphs and not for larger ones, right? So the probability, initially the probability is good. Okay, the probability that your edge, the collapsing edge, does not belong to the min-cut is good. It's 1 minus 2 over n, which is really good. It only becomes smaller when your graph sort of shrinks and becomes smaller and smaller and smaller. So at that time, you want to boost the probability. What we are doing is doing it in a very naive fashion. We are going to do, we're just going to repeat the whole thing n square log n times. There's no need to do it. We only need to repeat, okay, when the graph sort of becomes smaller. So here's an idea to do that. Okay. So suppose we keep collapsing vertices until the number of vertices in the graph becomes n by 2. Okay. Now what is the probability that a min-cut C has survived until that time when the graph has n by 2 vertices? Okay. So again, we do the same calculations as before, and it turns out that this probability is going to be greater than equal to 1/4, right? So the probability, so instead of collapsing it until the graph has 2 vertices, you collapse it until the graph has n by 2 vertices. Same calculations hold, and the probability that the min-cut C is going to survive in that n by 2 vertex graph is going to be greater than equal to, you work this calculation out, you get a similar kind of calculations where things get cancelled, and this turns out to be greater than equal to 1/4.
I have a question here. Though I think logically it sounds pretty correct that you're talking in terms of the number of vertices when you're talking about the size. But when you look at the probability of whether an edge pick belongs to the cut or not, you're actually considering the edges, right? cut consists of the edges and the denominator is also the total number of edges in the graph, right? So, isn't it a little counterintuitive in that sense? Because as you keep shrinking the graph, the total number of edges keeps reducing. The total number of vertices is of course reducing, but the number of edges is also kind of,
So here's the problem. You're right, but here's the thing, right? As we keep on shrinking, we have a handle on what is the number of vertices in the shrink graph. There is a problem, right? So if we try to track the number of edges, that becomes an issue, right?
yeah, that's an issue, but so what I'm trying to say is that probably suppose what you started with was a very, very sparse graph in terms of the number of edges. So maybe there were, say, n vertices, but the number of edges was much, much smaller than n square. And there were very few, say, linear edges or something. So as the number of vertices come down, the edges with respect to the number of vertices is actually rising.
Okay, yeah.
Right? So maybe I'm not explaining the question pretty well.
No, that makes sense,
Does that
yeah.
make sense?
Yeah. And okay, so and then you want to claim that their probability even gets better and better.
Exactly.
But getting a handle on how many edges survive, that might be an issue, right?
Yeah, of course, that I understand.
So I don't know. So there are pros and cons, and if you don't have a handle on the number of edges that are surviving, then doing an analysis like this becomes very messy.
For that matter, you may have all the some n-1 edges surviving.
Yeah.
All the vertices on one side, everybody is connected to this. We don't know, like. how many-
Right. Yeah. So we don't have a handle on the number of edges surviving, right? So but it's yeah. So that's a good observation, though. Maybe you can think about it. So I don't know any analysis of min cut. Maybe there is. I don't know personally analysis based on the number of edges.
Yes, one of these elements is fast enough in the beginning. We are really collapsing the vertices which are connected. So, for that matter, there will be several vertices which will not be able to collapse otherwise also.
No, graph is connected.
The graph is connected.
Graph is connected.
Otherwise, yeah, the graph is connected. Otherwise, the problem is simple, right? So we can.
Even if it is a connected graph, like it could be one vertex in the center and all the vertices around it which are connected to the center. It's a connected graph.
Yeah, so what's the doubt?
What I mean to say is that the proportion of the number of vertices with respect to the ratio, how many edges are there and how many vertices are there.
So you're supporting her idea or?
I'm confused. I'm confused in the sense that probably that may work out or it may not work out is not very clear.
Her idea.
No, that, I'm not saying that I know that we don't have any track of the edges that remain, but what I'm saying is that
Yeah, or your observation makes sense. Yes.
isn't that a more logical parameter to think in terms of?
Sometimes it is more logical, but then if you don't have a handle, analysis becomes extremely difficult, right? So here we have a very clear that at every round we know the number of vertices. If we do analysis based on number of vertices, it becomes easier. But your observation still is holds. Okay. So what we'll do is the following, right? So starting from G, we run iterative collapse procedure 4 times independently to obtain graphs G1, G2, G3 and G4 that are n by 2 vertices, and then repeat this step in a tree-like fashion. So break it into 4 and each of them again break it into 4 and again each of them break it into 4. So until you get, and then eventually at the leaf where you have 2 vertices, you pick the sort of the best one. Okay, and if you run this, if you do the analysis of this running time, then you get reconciliation of this, the following form: TFN is equal to 4, TFN by 2, order n square. The running time you get out of this is going to be order n square log n. The success probability, if you work out, it's slightly tricky. So the success probability works out to be, again, you can form a recurrence relation with respect to the probability of success, and it looks something a little bit messy like this, but if you work it out, then the probability of, right? These kinds of algorithms which always produce the correct answer are called Las Vegas algorithms, and the second kind of algorithm which which produce an incorrect answer with some small probability are called Monte Carlo algorithms. Okay, so and there is an interesting relationship between Monte Carlo and Las Vegas algorithms. Let's see that relationship. So we have the following theorem, and I'll ask you to sort of fill in the blanks, fill in what should be there in this particular theorem. So you are given a Monte Carlo algorithm for solving a problem that runs in time, in expected time t of n, and a success probability of gamma of n. Further, given a solution, there is a deterministic algorithm that can verify, and a deterministic algorithm can verify the correctness of the solution in time t of n, small t of n. Then there is a Las Vegas algorithm for the problem that runs in time, in expected time. Can you complete this theorem? So it's a longish statement, so just parse it and let me know what the blank should be. Okay.
So that's the amount of work you're going to make one run and then check for correctness.
Okay.
Right? And then this is the, and then the probability with which you get a positive mistake, which you get success is gamma n. So it's actually like
Gamma is times Tn plus
gamma t
2 Tn gamma n 1.
Give me the expression.
So suppose you get success in the first go.
Okay.
Then the amount of time that you have spent is
Tn capital expected time. No, why gamma n? Gamma is the success probability, right?
Success probability. Okay, sorry. Plus Tn.
So Tn plus Tn. Okay. So if you get the correct answer in the first go.
If you get a wrong answer in the first go, then it's 1 minus gamma n into Tn plus Tn
Okay.
into 2 into Tn plus Tn, because then you have to have another
Okay.
this thing.
Okay. So you are calculating the expected times, right? So gamma n plus 1 minus gamma n. Okay. So T2 into Tn plus Tn
And
into gamma n, right?
gamma n.
And otherwise you will again have gamma n 1 minus gamma n whole square into 3 into Tn plus Tn and so on and so forth, right? What do you think this expression resolves to, simplifies to? Try doing it, taking things out common, and maybe you can. There's another way, nice way of looking at it, right? So, and maybe we look at it both ways. So, what is the expected number of times you have to run the experiment before you get the correct answer? What is the expected number of steps, number of times that you have to run? No. So look, you have a Monte Carlo algorithm, right? So you want to produce a Las Vegas algorithm. That means you want to output a given algorithm that always produces a correct answer. That means you have to repeat the Monte Carlo algorithm until you get the correct answer.
You make it till infinity.
Yeah, we'll do it until infinity, right? And then do the summation, right? So that's one way to think about it. Another way to think about it is how many number of times do you need to run this Monte Carlo algorithm, expected number of times, before you get the correct answer? 1 upon gamma n, right? So the running time should be Tn plus, so it should be Tn plus Tn by gamma n, right? Okay, this is what you should expect to get. Okay, so now again a discrete math question. Can we solve this to get that expression? Should we do that?
Sum of GP when it comes.
Right? Okay, so let's do it, right? So we'll take in each of these, we have these terms Tn plus Tn, right? So let's take it outside, okay? And gamma n is also there, so let's take it outside, right? So you have gamma n, okay? And you have Tn plus Tn. right? And you have, now you have 1 plus 1 minus gamma n plus 3 into 1 minus gamma n squared plus 4 right? So what is this? What is this?
Arithmetic or geometric.
Okay, so what does what does this give you? So if you do that, then what the expression, the simplified, the closed form expression?
So you denote this by Gn and then you compute 1 minus gamma n into Gn.
Okay, so it will give you, this will resolve in 1 by gamma n whole square, right? So gamma n cancel, this is the expression that you get, right? So that is what you get. Okay, so there are multiple ways to do it, both of them will give you this expected term. Okay, that is all I want to talk about. If there are any questions, then I can take the questions. Mhm.
Why this particular nomenclature?
No, I completely forgot. Somebody did tell me a story about this.
Why the chance of gambling and multi-colored TV?
No, there was some interesting story. Sorry, I forgot the story. But do a wiki search. I think pretty sure that somebody would tell you about the story. Say it again.
Can you apply in big data analysis?
Yeah. So suppose right. So the way you basically want to cluster the data, right, in big data analysis. That is the first step of data analysis, right? So you define the relationship between pairs of data. That means you define distance between pairs of data. And right now, or whether the two data points are connected or not, you define a graph. And then if you find the min cut, then you can, in an iterative fashion, you can cluster the graph using min cut. That's exactly what they do in many of the clustering, graph clustering scenarios.
Anything else? So thank you, Dr. Jasper. Your talk on randomized algorithms very deterministically motivated many of us to learn more about randomization. Thank you very much.
Thank you.